All right, Abby, here we go. Let's take a look. This one we have to what? Show that the area of the shaded region is 8 sine x minus 2x. Okay, fine. So, the first thing that we're going to do is label this stuff. They tell us that this angle here is x, the radius of the inner circle is 2, and the radius of the outer circle is 4. So boom, boom, boom. Okay. So let's see. Well, I think you'll agree that the area of the shaded region, area of shade, throw some shade, slaying, equals, that makes no sense, equals the area of triangle POQ, right? Whoops. Area of triangle POQ minus the area of the sector. I forgot to label it. I'll call this A right here, and I'll call this B, sector AOB. Okay, so triangle, big triangle, whoop. And if I cut out this, I'm left with the shaded area. Okay, so from your formula sheet, there's a formula for the area of a triangle, which is 1/2 AB sine C. So this would be 1/2 times 4, the length of OQ and OP, times 4 times the sine of x, the included angle right here, whoop, minus the area of sector AOB, also in your formula sheet. The area of an arc or of a sector is 1/2 r squared theta. So that's going to be minus 1/2 r squared times theta. Now the sector is the smaller circle, right? So that radius is 2. So 1/2 r squared would be 1/2 2 squared times the angle x. And let's clean that bad boy up. 1/2 times 4 is 8 sine x. Minus 1/2 of 4 is 2x. Can I get a booyah? Boom, 8 sine x minus 2x. Okay, so that's part A. Boom. And then part B says find the maximum area. Well, in calc, when we want to find a maximum, we find the derivative. So, and find the value of x or the value of theta that's going to maximize this sector's area. All right, so A max or A prime would be 8 cosine x minus 2. That's the derivative. So to find the critical point, set it equal to 0. We would get cosine x equals 1/4. And so then arc cos, this would be a calculator question for sure. Arc cos of 1/4 is approximately equal to, calculator time. Oh, hold on, I had something messed up. Sorry. Okay. 1.3812. So 1.3812 ... And I didn't round it because I'm not done yet. They asked for the maximum area. Now you could do critical points here, but there's only one critical point, so that has to be the one that gives you the max. Like you could do a sign diagram and to the right and to the left and put it into the derivative, but you're fine. You're in the quadrant. Cosine's positive, so you could put it in and do the unit circle, but you do have a calculator, so you could graph it and see it's a maximum as well. You don't have to show it since there's only one. Anyway, so that maximum area, I'm just going to plug into the area formula. Boom, right there. So that would be 8 cosine, and you want to use a bunch of digits just to be accurate. 1.3812 minus 2 times 1.3812. And we cranked that Soja Boy into our calculator, and I believe we get 5.12. Okay. Slay. I don't know what's the matter with me. All right, so now we get this ridiculous candy box thing. And there's a lot to do here. First, we have to show that the area of each hexagon is what? 3 root 3x squared over 2. And we know the base is x. So, part A. I think you would agree that the area is of each hexagon, area of hex. Since it's regular, all of these triangles are exactly the same size. There's 6 of them. That means that all of the angles in the triangle are 60 degrees because 360 divided by the 6 angles here are 60. And we know that it's an equilateral triangle because it's a regular hexagon. So let me get rid of all of that nonsense. Okay, so that means the area, the entire hexagon would be 6 times the area of a single triangle. All right, so here we go. So I'm going to pull out one of those triangles. Wonk, wonk, wonk. And we know they're all of side x. Yep. And we know they're all 60 degrees. So if I drop me a perpendicular, I've got myself a 30, 60, 90 triangle. This entire length here is x, right? So now, oops. Yeah, this entire length is x, which means this bottom guy is x over 2. And because we have a 30, 60, 90 triangle, we know the relationship that the longer leg is equal to the shorter leg multiplied by root 3. So x over 2, or x root 3 over 2, or root 3x over 2. So the area of a triangle, well, first I'm going to put the 6 in front because there's 6 of them. The area of the hexagon is 6 times the area of one triangle, which is base times height over 2. So here we go. The base is x. The height is root 3x over 2, right? Right there. All over 2 divided by 2. Base times height divided by 2. Winning, just a little bit of song, a little dance, 1, 3. And what do we get here? We get, just like they said, 3 root 3, 3 root 3, x times x is x squared over 2. So we did it, and that 2 comes from here, right? That 2 comes from there. So we have satisfied part A. Okay. Now, given that the volume of the box is 90 cubic centimeters, show that when x equals cube root 20, right, the total surface area of the box is a minimum, justifying that conclusion. All right, so first of all, let's say that the surface area would be equal to the top and the bottom, right? The top, the area of the top, and the area of the bottom. Now, we already know that the area of each hexagon, the top and the bottom, is 3 root 3x squared over 2. So I've got 2 of those. So 2 times, let's see, 3 root 3 x squared over 2. We're going to get nice cancellation here in just a second. plus the area of the sides. Well, there are 6 sides. They're all rectangles, all the same size. So that's going to be 6 times x. Uh-oh. I'm going to call this h for height, the height of the rectangle. So 6 times x times h. So we have a formula for area. So that's going to be the 2's cancel, bang, bang. 3 root 3 x squared plus 6xh. And this would be lovely. All we would have to do is take the derivative, find our critical point, see that it is cube root 20, and life would be great. But our problem is, oh shoot, we need something for h. Ha! They tell us a volume, don't they? They tell us a volume. They tell me that the volume is equal to 90. And the volume of any regular figure is equal to the area of the base multiplied by the height. So we know that 90 is equal to the area of the base, which is already 3 root 3x squared over 2 times the height. So to find the height in terms of x, we're going to divide both sides by 3 root 3 x squared over 2. We could also multiply by the reciprocal. That would be a little easier. 2 times 90 over 2 times 90 over 3 root 3 x squared equals h. Okay. So 2 times 90 is 180 divided by 3 is 60. So we get, I'm going to give myself some room and write that as 60 over 3 or root 3 x squared, which I'm going to go ahead and write as x to the negative 2. Because we know what's coming. We're going to have to take a derivative here. So I'm going to say 60 over root 3 x to the negative 2. This is just fantastic news, abs, because now we have a full formula for our area. Area equals 3 root 3 x squared plus 6x times 60 root 3 x to the negative 2. Let's clean that bad boy up. Area equals 3 root 3 x squared. What's going to happen here? We're going to get 6 times 60 is 360. So plus 360. Yeah, plus 360. X times x squared is x to the negative 1. Nothing happens with the root 3. There we go. All right, so now we're ready to take a derivative, right? So a prime is equal to 6 root 3x minus 360 over root 3 x to the negative 2. 6 root 3 x, 6 root 3x, come on, Dave, minus 360 over root 3 x to the negative 2. Okay, so I'm going to rewrite that as, well, I'm going to set it equal to 0, right, to find our critical point. 6 root 3x minus 360 over root 3x squared. That's just going to make it easier to solve. Okay. So now solving, we get 360 root 3 x squared equals 6 root 3x. If I multiply both sides by root 3x squared, I get 360 equals 6. Root 3 times root 3 is 3. X squared times x is x cubed. 360 equals 18x cubed. Divide by 18, booyah, we get 20 equals x cubed. So our critical point is cube root 20, if you recall. They said to show that it's at a minimum at x equals root 3. Okay? So, I think perhaps that we will go ahead and take the second derivative, because if we can show that the second derivative is always positive, I got a fly flying around here, then we know that that it's always concave up. So if we find a critical point, it must be a minimum. Okay, so that's a down and dirty way to do it. So here's a prime right here. So the second derivative is going to be what? 6 root 3. That's positive. Whoop, whoop. A negative 2 times a negative 1 is a positive 2. So we are in business. We'll finish it out, though. So 2 times 360 root 3 x to the negative 3. Now, don't let the negative bother you. Remember, that would just become x cubed down low. That will always be positive. 6 root 3 plus 2 times 360 over root 3 is always going to be positive, because 6 root 3, you know, with the dimensions of the blah, 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 with cube root 20, it's always going to be positive. So we can say the reasoning would be the second derivative is greater than 0, right, when x is equal to cube root 20. And you might say, hey, Dave, couldn't it be negative? If we had a negative value of x, couldn't this be negative? Well, x is a measurement of length, so it can't be negative, right? So we can say a double prime is greater than 0 when x equals cube root of 20, right? Hence, maybe, I don't know, concave up, which gives a min, which means x is a min. All right, hope you enjoyed it. I certainly did. Peace out, keep slaying.